Welcome to this session for communication system. In the previous session we discussed about different schemes of modulation like amplitude modulation and the angle modulation, where we have seen the different cases of double sideband suppressed carrier, single sideband, double sideband large carrier, vestigial sideband modulation. Then in angle modulation we have seen the frequency modulation and the phase modulation. We have also seen that the receiver side there are four different kinds of receivers. One is the coherent receiver or coherent demodulator, and then the envelope detector, envelope demodulator. Then we have phase detector and the frequency detector for phase modulation and frequency modulation. Now we have to see at the receiving end, we will be going to the receiver and seeing that one special kind of receiver that is present everywhere nowadays, and that is called a super heterodyne receiver. So the topic of discussion today is in this session is the super heterodyne receiver. We need to understand why it is required, and if this would have not been there, then what would be the case, and what are the problems that is associated with the receiver during this early development of its stage. But now those problems does not exist at all, because all the things are taken care of properly. So the main topic is again communication systems. Subtopic in this is super heterodyne receiver. See, at the receiving end, generally we pick the signal through the antenna, right? An antenna will receive the frequency of large band. Generally they can, if it is in VHF antenna, then it will pick all the frequencies present in the VHF range. Or if the antenna is working in the frequency range of UHF, then all the frequencies coming in the UHF range it will pick up. But in VHF band itself we have many channels, right? Not a single channel. That means antenna is picking all the channels. That's the thing. Now if you want to see a particular channel, then what we should do? The idea is you put a band pass filter that only that particular frequency will be allowed to pass, and then you process it by demodulator, and then the demodulator output will be your baseband signal. But if that is the case, then we need to have tunable band pass filters, and whatever the center frequency is coming FRF from it, that will be every time different, and the demodulating circuit is dependent on now center frequency FRF, because different channel will have different center frequency. So demodulation is process depends on the center frequency, so that will also keep on changing. So if that is the case, that becomes a very impractical kind of situation where your cost of the receiver increases drastically, because you need number of demodulators for each frequency band, and then tunable band pass filters, and size, cost both will increase, which is a very undesirable feature for a receiver. A receiver should be simple, receiver should be cost effective, and if it is small in size, then it's best. So what to do? How to make a receiver which is independent of the incoming signal frequency, right? So that's where the super heterodyne receiver comes into picture. The demodulation circuit is totally independent of what frequency is getting transmitted. It depends only on the intermediate frequency, which is one frequency which is generated at the output of the super heterodyne. So let's see that what is a super heterodyne circuit, and the block diagram, and then how it actually works, and the problem associated with it. Okay. Antenna. We need to understand the meaning of why it is super and heterodyne. Okay. RF amplifier. FLO, that's called local oscillator. FIF, intermediate frequency. oscillator, demodulation, then the baseband oblique message signal. So let me write here. Incoming radio frequency, local oscillator frequency, intermediate frequency. Okay, so these are the terms which is associated with a super heterodyne receiver: FIF, FLO, FRF. Okay. Signal is coming from all directions. I'll just tell you that some example of radio frequencies and the intermediate frequencies. If you look at AM signal, AM modulation, okay, there FRF range is from 550 kilohertz to 1650 kilohertz, and FIF is 450 kilohertz. Okay, that is for AM. For FM, many of us know FRF range is 88 megahertz to 108 megahertz, and FIF in this case is 10.7 megahertz. Okay, there is a reason for choosing this FIF. Now, based on FRF and FIF, LO frequencies are generated because that is present within the super heterodyne receiver. So this is the output, this is the present in the super heterodyne receiver, this is the incoming signal. Okay, so this is of course not totally in our control, but this is totally in our control, FLO. Now, how this FIF comes into picture? This FIF is basically the sum or the difference of FRF plus FLO or and FLO. So this FIF, it is FRF plus FLO or FRF minus FLO. Or it can be FLO minus FRF also. So that is the thing. Now, if you this is called up conversion. The reason being this frequency is greater than FRF, right? FIF will be greater than FRF, and this is called down conversion. Now the frequency is reduced in this case. Let's see, 88 megahertz to 108 megahertz high frequency, and FIF is 10.7. That means it is down conversion. Generally, in the receivers, what we design for commercial applications, the FIF is lower than FRF, and the reason being, if you process the low frequency, the cost decreases, right? That is the reason behind it. Now, how this actually works is, it is a simple mixer, means different other frequencies also get generated because of a nonlinearity present in the mixer, but it's a product. It is just cos, if I multiply cos 2 pi FRFT into cos 2 pi FLOT, then as you know I am going to get 1 by 2 cos 2 pi FRF plus FLOT plus 1 by 2 times cos FRF minus FLOT. Okay. So two frequencies are generated. So this is FRF minus FLO or FLO minus FRF. That's why I have written this mod. It can be anything. Now let's see how it actually works. How this particular mechanism makes the demodulation process independent of FRF. It depends only on FIF. Okay. So for different FRF, FIF is same, right? Let me just take one case. Some hypothetical situation. Let's say there are 5 channels present. Okay, now this is channel 1, channel 2, channel 3, channel 4, channel 5. They all are transmitters. Okay, they all are transmitters. So they all are transmitting the signal in the free space. Now channel 1 frequency ranges from 100 to 105. Channel 2 is from 105 to 110. Channel 3 from 110 to 115. This is from 115 to 120. This is from 120 to 125. Okay. These are the center frequencies. 102.5 the center frequency for this, 107 center frequency for this, like this center frequency. So this becomes FRF, and the bandwidth of each channel is 55 megahertz. Generally, that is the bandwidth for the TV channels. Okay, that's why I taken this 55 megahertz. Now all the frequencies 1, 2, 3, 4, and 5, they are coming at the receiving end. That means receiving antenna. They all are going into this. They all are getting amplified. Finally, all frequencies are available here. Now I have to choose FLO in such a way so that when I want to watch channel number 1, its corresponding FIF is generated. Okay, remaining all FIF are away. So let us choose FIF also. Let's say FIF in this case is 10 megahertz. So to get 10 megahertz, and it is a down conversion process, because conversion we will never get, because these all are high frequency and I want to go to 10 megahertz, that means I should get less frequency. So FLO should be what? Now two possibilities exist in this. One is it can be either 92.5 or it can be 112.5. Right? In this case 97.5 or 117.5. In this case it is 102.5, 122.5. In this case it is 107.5, this case 127.5, and finally for this one it is 112.5 or 132.5. So you can choose this set or you can choose this set. Whichever set you want, you can choose set. So let us make use of the first one. Okay, so my FLOs are this, my FRF is this. Now correspondingly you see what will happen now. If I want to watch channel number 1, then I will generate 92.5 in the FLO because it is in my control. So I press channel button 1. This will correspond to generation of FLO of 92.5. 92.5 will mix with all the 5 frequencies. So 92.5 will give me, corresponding to this, it will give me 10 megahertz. Now just see here, 10 megahertz for first channel. For second one it will give me 15 megahertz. Then for this it will give me 20 megahertz. For this 25 megahertz. And for this it will give me 30 megahertz. Right? Now 5 frequencies are available at this point. Now what is there next? Then next is a filter. IF filter and IF amplifier. Now what IF filter will do? IF filter will allow only 10 megahertz to pass with bandwidth of 5 megahertz, right? Remaining all will get filtered out. So IF filter is working presently in this case is from 10 megahertz with a bandwidth of 5 megahertz. Okay? So this will allow only this, remaining everything will get suppressed. So finally you will get the baseband message signal corresponding to channel 1. So this is fine. Similar thing will happen with this channel. Suppose if I want to watch 122.5 or channel number 5. So channel number 5, I'll generate this FLO 112.5, right? So 112.5 when mixed with, I'll write this again. See the result. 112.5 when mixed with 122.5, it will give 10 megahertz. 112.5 when mixed with this, it will give 5 megahertz. This one mixed with will 0, 5, then again 10 megahertz. Now you see the problem. Both channel 5 and channel 1 giving me the 10 megahertz. And my IF filter is also 10 megahertz. That means the message, the signal corresponding to channel 5 and signal corresponding to channel 1, they both will overlap and they will pass through this IF filter amplifier. That will lead to nothing but interference because the carrier is not orthogonal in those cases, carrier is same. So that's become a problem. Now at the demodulator output you will get nothing but the interfered signal, interfered message signal. This is a problem. This problem need to be avoided. And how to avoid this problem? Let us see this. Now this problem is called the problem of image. The image frequencies or the image signal which is occurring in the receiving chain. So you can say when channel 5 is there, instead of choosing this, let's choose this. Yes, that's a good idea. That means you have to plan your FLOs accordingly. You cannot choose any FLOs, but you have to choose the FLOs such a way so that the image frequency problem is resolved. Right. In that case, you can use this. But suppose now if this is available FLOs, then how to decide, how to get rid of this problem? Now, what is the issue here is that all the frequencies are present here, right? All 5 channels are present here. But if I do something and if I could be able to make that only the channel which is required that is available, remaining all are not available, then the things can be solved easily. That means what? It means what? Some kind of pre-selection is required at this stage. Okay, so only that channel will be passed which is allowed, which we want to see, remaining all will get suppressed. Now what is this pre-selection? Pre-selection is nothing but a band pass filter. Pre-selector. Pre-selector is a term generally used in this. This band pass filter is operating at these center frequencies, these FRF center frequencies with the bandwidth of 5 megahertz. Okay, so band pass filter characteristics are like this only. Only thing is that now this becomes a case of a tunable band pass filter. Tunable band pass filter is a filter whose bandwidth remains same, but the center frequency keeps on shifting depending on the channel. Okay, depending on what we have decided. So if I want to see channel number 5, then the band pass filter will allow only this, remaining everything will get suppressed. Right? Only this will be passed. Now when this is passed and when you mix with 112.5, you will get 10 megahertz corresponding to this. Remaining everything will be there because they all are suppressed already. Okay. So this is one way of removing the problem of image. Now let us see why I am calling it image and why not some other issue. Let's see, because it's like an image only which happens in the mirror. When my FRF is 122.5, so FRF is tending here 122.5. Okay. This is your FRF and FLO is 112.5. So let's say this one is FLO. Okay. Now what is the distance of this? The distance of this is 10 megahertz. Now if I see image of this, this will fall again 10 megahertz away from here, and that will come at 102.5 megahertz. Now you see, this channel 1 is an image for channel 5. Vice versa also true. If this is the actual one, then image will fall here. In that case, if FLO, if I choose 112.5 here for this one, then channel 5 will become an image. Okay. So that's why the name given to this is image, and this acts like a mirror. Of course, there is not like mirror frequency, but this acts like a mirror and the images fall over here. So this is F image. Now we can derive the relationship between F image. How to derive an F image for this? So you can just see here, if FRF is greater than FLO, that means this case, then F image is FRF minus 2F IF. FRF, FIF, FIF, that means 2FIF. So that becomes FRF minus 2FIF. Or it is nothing but FLO minus FIF. That is also true, right? Because FRF minus FIF is FLO. So FLO minus FIF, that will also give the image. So this is one relationship. Other ways, if FRF is lesser than FLO, then F image is FRF plus 2FIF, right? FRF plus 2FIF, FLO plus FIF. Okay, so this is the relationship of image frequencies. And the image frequencies can be removed using preselector is one technique. That means use a preselector. What could be the other technique? The other technique is a selection of FIF. If you choose the FIF in such a way so that the image frequency goes out of band, then image problem is resolved. If you just recall, okay, just see, and there are one FM band which is present from 88 megahertz to 108 megahertz. Okay. Now this is your FRF. Right, this complete range is FRF. What should be the FIF? So that if I am standing here, the image should fall beyond this. Okay, let's say that is FIF, which is question mark. And when I am standing here, FLO must be here. So FRF is lesser than FLO. So F image is nothing but 88 megahertz plus 2FIF. I don't know what is FIF. And what should be F image? F image should be at least 108 megahertz or beyond. So F image should be greater than or equal to 108 megahertz. Actually, it should be greater than 108 megahertz, right? So 88 plus 2FIF should be greater than 108. This implies 2FIF must be greater than 20. This implies FIF should be greater than 10 megahertz. Now you should understand and appreciate that why we have chosen FIF of 10.7 megahertz in the case of an FM signal. Of course, some guard band is required. FIF should be greater than 10 megahertz. Greater than 10 megahertz we have chosen, that is 10.7 megahertz. So all the problems of guard bands, some spectral leakage, everything will be solved if I choose this FIF. So this is one way of selecting the FIF. Now here the filtering and other things are not required. because one filter of 88 to 100 megahertz is just sufficient. Okay. Remaining band pass filters are not required. Okay, let's move ahead. Let us take some problems. Achha, why it is called super heterodyne receiver is, in a microwave circuit or in any circuit which is working at the microwave frequency range, if a component does more than one work, that means here if I use only a mixer, only this part, then it is called heterodyning, because this and this are two different frequencies and you're trying to mix two different frequencies. That's why the name heterodyning, hetero. Now this particular thing, this super heterodyne receiver, is a circuit which is this one. It is doing the amplification also, it is doing the mixing also, it is doing the filtering action also. So it does multiple action. That's why the name super. Okay, because something which is doing extra, something which is doing more than the normal things, and that generally called a super, right? So that's why the name given to this is super heterodyne receiver. It does multiple things, right? So this is a block diagram for a super heterodyne receiver. What it is actually doing, it is just shifting the carrier frequency. It is shifting the carrier frequency from FRF to FIF. FRF is some carrier frequency, but FIF always remains same. So it is assume that you are coming in a city, in any city from some other city, either in an aeroplane, right, or you are making use of train, or making use of a bus. So they all are different carriers. But finally, when you want to go home, you are taking nothing but a taxi. Every time, whether it's aeroplane or train or bus, finally you're taking taxi only. So taxi is same in all the cases, but these three carriers are different. So here also FRF are different, but FIF remains same. Passenger sitting in the taxi is different. So the message signal present in the FIF is different. So that is what, they just shift the carrier frequency. So carrier nature is changed. The carrier is earlier this, now the carrier is this. But the passenger in this and passenger in this are same. Okay. So message signal does not get interfere, only the carrier changes. Okay. See this. The intermediate frequency. local oscillator FLO are chosen such that it is required that image frequencies fall outside 8 megahertz to 68 megahertz band. The minimum required FIF in megahertz is dash. Okay, so we have to find out what should be the minimum value of FIF so that the image frequency problem is resolved. Now this has got a relationship that we can see, and we can use that relationship always to find out the FIF. Let's see what is that relationship. The simple relationship. Suppose this is F1, let's say this is F2. Now let's say FIF is required, is what we want to know. Now we know that the image F1 plus, if I am standing here, then the 2 FIF must be greater than F2 so that the image falls outside this. This implies FIF should be greater than F2 minus F1 upon 2. Okay, same thing as came in this case also. 88 megahertz, 108 megahertz minus 88 megahertz divided by 2, FIF should be greater than 10 megahertz, right? Same thing will come over here. So that becomes a relationship. This we should know. Now the case has become very simple. In this case, the F1 is 58 megahertz, F2 is 68 megahertz. So the minimum FIF should be greater than 68 minus 58 divided by 2, that is equal to 5 megahertz. Okay, FIF should be greater than equal to greater than 5 megahertz. The minimum value is 5 megahertz. That's it. So that we should know. Okay, let us do one more problem. For a super heterodyne receiver, the intermediate frequency gigahertz. If the frequency of received signal is greater than frequency, then the image frequency in megahertz is dash. Okay, so I think the image frequency is asked, IF is given, FLO is given. So already we have seen if received signal is greater than the local oscillator frequency, if FRF is greater than FLO, then the image frequency is FLO minus FIF. Okay, that's it. You just have to make use of this relationship. Please be careful, it is 3.5 gigahertz and this is 15 megahertz. So convert this into megahertz, because in hurry we sometimes forget to do this conversion. And here FLO I can write 3500 megahertz. F image will be 3500 minus 15, 3485 megahertz. Okay, 3485. That is the answer. Just see, the local oscillator means I am standing here and we want to know the image frequency. FRF is greater than this, so image will fall this side. So FLO minus FIF will give me the image frequency. Let us take one more problem. Super heterodyne receiver is to operate the frequency range of 1650 kilohertz with the intermediate frequency of 450 kilohertz. Let R is equal to C max by C min. denote the required capacitance ratio of the local oscillator, and I denote the image frequency in kilohertz. Incoming signal. If the receiver is tuned to 700 kilohertz, then (4.41) I is equal to 1600, B 2.1, I is equal to 1150, C R is equal to 3, I is equal to 600. Let us solve this. Now what happens here is that capacitance and how they are coming into the LO frequency. As I said, if you look at this, FLO is an oscillator, and this oscillator, how it works, it has some inductive or capacitive circuit, and you know that the frequency F0 is nothing but 1 upon root LC. That means the local oscillator frequency FLO is proportional to 1 by root of C. Okay, so when FLO is minimum, C is maximum, right? And when FLO is maximum, C is minimum. So FLO max by FLO min is equal to 1 by root C min 1 by root C max. So that will become root of C max by C min. So I can write C max by C min is FLO max by FLO min whole square. Now FLO max FLO max. So FLO max will come when the FRF is highest. So FLO max will be 1650 plus 450. So that is 2100 kilohertz. And FLO min corresponding to minimum FRF, that is 550 plus 450, that is equal to 1000 kilohertz. Take the ratio of the two and substitute in this. So this implies if I substitute in this will be 2100 by 1000 whole square, that is 2.1 whole square, 4.41. So if you look at the option, only option A satisfied. Let's find out I also. So since FLO is greater than FRF, so F image is FRF plus 2FIF, FRF is 700 kilohertz plus 2 times of 450, that is equal to 1600 kilohertz. Okay, so correct answer is option A only. That's how we can choose. This question came in GATE 2003. Okay, not a recent this thing, but yes, this F image, FLO, and finding this is a very common problem. It is coming regularly. We should understand this as a basic understanding of a super heterodyne receiver. We should understand this. See, your TV receiver is a super heterodyne receiver. Your set-top box is a super heterodyne receiver because output of the set-top box is a message signal, right? The baseband signal, which goes into the AV input of the television, audio video input of the television. See, one more question, of course not related to the super heterodyne receiver directly, but at the transmitting end, if you have number of channels, then how to find out the overall bandwidth? Let us see that. Ten real band pass message signals, each of bandwidth 3 kilohertz are to be frequency division multiplexed over a band pass channel with bandwidth B kilohertz. The guard band between the two adjacent should be 500 hertz. If the guard band in between any two adjacent signals should be of 500 hertz width, and there is no need to provide any guard band at the edges. Of the band pass channel. The value of B should be at least So each is having a bandwidth of 3 kilohertz, and in between there are guard bands of 0.5 kilohertz, 500 hertz. So let's see that how it is happening, and then we can find out the overall bandwidth. So there is a 3 kilohertz and then guard band of 0.5 kilohertz, then 3 kilohertz, then guard band of 0.5 kilohertz. Like this it is present till the end. Guard band of 0.5 and this one of 3 kilohertz. Okay, so we need to find out the overall bandwidth. So I can say this is present 9 times and 3 kilohertz is present 10 times. So overall bandwidth is 3 into 10 plus 0.5 into 9. That will become 30 plus 4.5, 34.5 kilohertz. Okay, so that is the situation. Yeah, I think it matches with option B, 34.5 kilohertz. Okay, so let us take a short break, then we'll continue with the session.